Hello, Raveen.
Hello, Johnny. Can you
How
hear
are
me?
you? Yeah, could you enable your video?
Yeah, sure. Give me a sec.
It seems like Will is not able to hear us.
Oh, okay. He's not able to hear us.
Hold on, we'll just check.
Wait, Will. Oh, no, he can't hear us. There's like a dialog box that opens that asks you to like where you want your audio to come from. So I think you might have clicked something different.
Hey, Raveen, could you tell Will to join in using computer audio? There's a button
Yeah.
that he has to press.
Okay. Do you want
Are you talking to him right now?
No.
Raveen, by the way,
Hmm? Yeah.
so you sent me these 3 worksheets, right?
Right.
So this one here, this one here. This is just duplicate, isn't it?
Yeah. They just do. I don't know. I think it's
Yeah,
meant to be. It's meant to be like a worksheet handout, so they can.
yeah. So they cut it in half, and then
Yeah.
yeah. Okay. So which question would you like to try? Do you completely understand the concept of mass defect and binding energy?
Yeah, I understand like more of that. I think what I'm struggling more is half decay and that type of stuff.
Half-life, is it?
Half-life, yeah, sorry.
Half-life.
And yeah, so we could
But,
do a
but
bit of it. Yeah, I think
okay.
we should just kind of wait until everyone else is.
Okay. Have you finished this worksheet? All 3 of them?
I finished the first 2. I don't think I finished one of them. Yeah, I don't think I've finished I finished alpha decay and beta decay. That one.
Okay. So this one is the
Oh, actually, there's actually one question that me and like some of my friends
hmm.
couldn't do.
Hey, Will. Hello. Okay, great. Can you say something?
Hello.
Yeah, we can hear you. So your microphone is working.
Yeah, that's what you know.
Yeah. Okay. So you've been doing decays and alpha decay, beta decay, gamma decay, neutrino. Have you guys also been doing anti-neutrino as well?
Yeah. That's
Positron?
it's not really like we're not really doing it. It's just like we're just
Yeah. Okay.
yeah.
And there is the gamma decay. So you guys have been introduced to the atomic mass number and atomic number, right? A and Z.
Yeah. Is
So,
Vish logging on? Vishal?
Vishal is not going to come today. I think
Okay.
he's feeling unwell.
Oh, okay.
Yeah. So, and you guys did binding energy. And were you guys introduced to this equation, mc square?
Yeah.
Yeah. Do you guys know what EV is? Kind of.
Yeah.
So do you guys know what joule is? Joule?
Yeah.
So just need to know that for now, 1.6 times by 10 to the power minus 19 joule is the same as 1 electron volt. So this is another type of unit of energy. You understand? So when you guys were doing the power pack prac, you know how when you run 1 kilowatt for 1 hour, this is a 1,000 watts, and 1 hour is the same as 3,600 seconds, right? Therefore, if you multiply these two, when you multiply these two, you get 3,600,000, and this is a power times by time. So therefore, this becomes work, and this is in joules. But we conveniently let this energy equal to So this is a 1 kilowatt, 1 hour. So we simply let it equal to 1 kilowatt hour. True.
Yeah.
So this is something like that. So EV is very good at measuring small quantity of energy. All right. So this is such a small quantity. All right.
Right.
Yeah.
So what is 1 mega electron volt? That is the same as 1.6 times by 10 to the power of minus 13 joules.
Yeah, okay.
So times by 10 to the power of 6. So that's a mega. This is
yeah,
also a small quantity as well. All right.
Yeah.
So here's the conversion. So you have 1 atomic mass unit. 1 atomic mass unit is about 1.66 times by 10 to the power of minus 27 kilograms. Did you guys learn that stuff?
Yeah.
So 1 atomic mass unit in kg is about this much. So this one is the size of like a small proton, all right?
Yeah.
A proton weighs about this much.
Oh, okay.
And then if you use the Einstein's energy equation, mc square, so mass is, we're converting this tiny mass into energy. So then we get 1.66054 times by 10 to the power of negative 27 times by the speed of light, which is 3 times by 10 to the power of 8 square. So if you do that, I'm just giving you the background for this one.
Yeah.
Maybe you guys already know this one. So until I fully identify your weaknesses and your strengths, tuition with me, I might be repeating stuff that you might already know, but we'll eventually get to know you better, and it won't be quite effective as we spend more time together. So here, this is the amount of energy in joules. When you convert this tiny, like a proton-sized mass into purely energy, this is the amount of energy that you get in joules. So that's a 1.49 times by 10 to the power of minus 10 joules. Now I'm going to divide this one by that quantity here. So I'm just trying to figure out how many mega electron volts fit into this quantity here. So I'm going to divide this one by 1.6 times by 10 to the power of minus 13, and voila, you get 934. So this one is 934. That quantity looks pretty familiar, doesn't it?
Yeah.
Yeah, so this one is, I think it's a 934.5, was it, or something like that?
It's 931.5.
931, is it?
Yeah.
So that's because the speed of light is actually 2.99 something.
Yeah. So
so you are actually, so this is actually, I should write it down, 931.5, is it?
Yeah. That's what
energy is what you get when you convert 1 unit of mass, 1 U or 1 AMU, into pure energy, right? Yep, it's all good.
Yeah.
So here's the thing. When individual protons and neutrons and electrons come together and to form an atom, right? So there's 1, 2, 3, 4. There's 8 of them. 1, 2, 7. There's 6. Yeah, there's 8 of them here as well.
Yeah.
Yep. So which one weighs more?
The one that's clumped up.
This one weighs less, right?
Oh.
This one weighs more.
Oh.
Wait, what?
So the difference is, so when individual protons and neutrons come together, they lose mass. All right.
Really? Okay.
Yeah. So this is known as the mass defect. So this is greater.
Oh yeah. So because of the energy is released when they.
Yeah. So when they come together, it becomes this clumped up stuff, and then some energy.
Yeah. So that's what we
Right.
do the alpha decay. Wait, Will, have you been doing alpha and beta decay?
So tiny bit
Yeah, yeah,
of mass. So actually, you guys need to know that this is a little bit different from alpha, beta, gamma decay.
Oh, okay.
This is a little bit different from. So this is a different topic from alpha, beta, gamma decay.
Wait, why is it way less though?
So it's just the way it is.
Okay.
So it's like the same question as why do we exist? Yeah.
Okay,
So it's just the way nature works. So if you gather lots and lots of individual protons and neutrons and electrons.
Wait, so it has something to do with the binding energy or whatever?
Yeah, that's right. Exactly. So when you combine these, so this is what happened. The universe started with lots and lots of protons and neutrons and electrons, okay?
Yep.
And they were all separated. And then they came together. But when they come together, it weighs slightly less than the original individual particles, okay? So there's a missing mass, right? There's a missing mass.
Yeah.
The missing mass is known as?
Neutrinos?
No. So forget about alpha, beta, gamma, neutrino at the moment, okay?
Is it the mass defect?
This is known as the mass defect.
Okay. So do we know what the mass defect is then?
We can calculate it. So all we have to do, so if you look at, for example, this question here, there's a lithium 7, and it says that this one weighs 7.016003, right?
Right.
So this one is made up of, so there's a lithium is number 3, isn't it?
Yeah.
So lithium is number 3, which means three protons, right?
Right.
So this one is made up of 3 protons, 4 neutrons, and must be how many electrons?
3
electrons, right? So we're going to calculate the mass of this, mass of this, and mass of that, and combine them all together, right?
Right.
Let's do that now.
So yeah, I think I also sent you this
the data, right?
Yeah.
There's a data sheet.
Yeah, there you go.
So this is the individual mass, isn't it? Hold on. These are atoms, not individual protons and neutrons.
For protons, we use the hydrogen one. So the mass of a hydrogen atom.
Okay.
No,
so hydrogen is made up of proton and electron, right?
Right.
Yeah. So we shouldn't be using that one.
But yeah, that's the one. That's the one they use in the worksheets.
Okay. So, but 1 proton. Oh, we can actually do this. 1 proton. So it's about that much.
Right. I think it's very close because electrons are like
Yeah, they're very close because electron is actually pretty much ignorable.
Yeah. Right.
Yeah. So we can kind of approximate it. We can take 4 of this, and then I just need to clarify something. You know how mass of a proton, 1 proton, is about 1.67. Let me just take screen capture of that. This here. So this is the mass of the 1 proton, true?
Yeah.
1 neutron is given by, so it's in your sheet. This one here. It's actually in different unit. I'm gonna ignore that. So 1 neutron in kilograms. I'm doing everything in kilograms at the moment.
Okay.
So you have 2 options. You can deal with kilograms, or you can deal with U. Okay.
Yeah.
And here's the thing: if you have a 1 U is equal to 1.66, was right here, right? 66054.
Yeah.
66054 times by 10 to the power of minus 27. So it's very close, right?
Right.
So if you divide this one by itself, of course you get 1 U, true?
Yeah.
So this is in kg, this is in U now. So if you divide this one by itself, that's at 1 U, all right? So U is always with respect to this value here. You understand?
Yeah.
So if I take a calculator and then type in 1.672621.898, and then I'm going to divide this number by this number here. 1.66054 then I get 1.00727, right?
Yeah, yeah. And then you got
That is the mass of the proton, 1.00727, but I'm just going to use so it might be slightly different from the data provided here. So your data here provides these two. So the bottom one for the proton and the upper one for the neutron. So I should actually...
Wait, hold on. I got a data sheet with the proton and electrons and stuff.
Okay, sure.
I'll send it.
Yeah, sure. You send it on the Facebook, please.
Yeah.
So the neutron is correct, this one here. But this is for hydrogen, so it might be a little bit higher. So we calculated about 1.00727. This one is saying 1.007825 because this is including electron. Okay.
Yeah.
Yeah, just waiting for your picture, Will.
Yeah. Just 1 second. Oh my god.
Whose dog? Whose dog's that?
That's fine. Alright. It might not be a good picture.
Okay, so 1 proton in U. So in U, it is... So you sent it. That's good.
Wait, Will.
I can also you look at the Wikipedia. So it's actually this one here. All right.
Yeah.
That's proton. So which is close to this value here, isn't it? Closer to this value. 727. That's right. 728. Yep. So that's the value of the U, all right, for proton. What's the electron? 1 electron in U. Let's figure it out. Mass of electron in U. So that's this much here. I'm not going to calculate the value of the electron. So if we actually combine these two, I think it's fairly close to this value here, isn't it? Which is, this was for the neutron. This one was for hydrogen. So
if you combine them, they'll become hydrogen.
Yeah, if you add these two, so 1.00727 plus 0.000548588, that's equal to 1.00785. Okay. So here's the thing. I'm just going to type it here. When you are counting mass of individual particles, you can combine proton and electron in hydrogen, and I have to actually, you don't have to write this down. Let me just phrase this one correctly. So what I'm trying to say is, you do not need to, hold on, let me just write this down. For hydrogen, which is, for hydrogen 1, not hydrogen 2, okay, which is made of 1 proton and 1 electron, there is no mass defect or negligible mass defect.
Wait, why? Oh, because
we just saw here. So this is the mass of the hydrogen, right?
Yeah.
This is the mass of the proton, mass of the electron.
Yeah.
So what I think where the mass defect comes from is from proton and neutron coming together. You know, electron is sort of outside, right?
Right.
But there is no mass defect with electrons. It only occurs with so for example, we're trying to do this question here, right? This one here. So for question 1, we have 3 protons and 3 electrons and 4 neutrons. So we add them all together, but we can combine these two and say, oh, this is the same thing as 3 hydrogen, 3 of hydrogen 1,1, not 2,1, not 3,1,
Yeah.
and 4 neutrons. So if you do that, it'll be exactly the same thing.
Oh, really?
Because there is no mass defect associated with the hydrogen 1,1.
But what's the point?
Proton
What's
and
the
electron
point?
come together. So that's why you were able to do just work with the hydrogen there and just ignore electron, because electron is part of it, right?
Right.
So there are 2 ways of doing it. You can do it this way, or you can do it this way. All right. So let's do it this way here. So let's do it in
Yeah, I think it's the way we're supposed to do it. So.
Yeah. So if this is the hydrogen there. So hydrogen is 1.007825. This one here. Times by 3, plus neutron is 1.008665 times by 4. So this is the mass of the individual. This is equivalent to the individual particles when they're all separated. 7.058135. 58135. U. Okay, and when they are combined together, you see how this is lost mass, so it's a 7.016003. So if you subtract,
Yeah, you get
then you get the mass defect. That's a 58135 minus 16003. That's 42132.
Wait, Will, do you struggle with like these type of questions?
No, not really.
Yeah.
No, but I don't mind.
Yeah.
No, so like
So this one, this is 7 is gone, right?
yeah.
So it's 0.0, and you times that by 931.5, right?
Yeah, to get the
Then you get this one.
And then you get
Johnny, I was actually struggling with question 3, I guess, of this.
Yeah.
That's the one like a lot of people couldn't do.
Question 1?
It's question 3.
This one here?
Yeah.
Okay. Let's try this. 2 isotopes of a certain element have a binding energy that differ by 5.03 mega electron volt. Okay, so it's the same element but 2 different isotopes, right?
Right.
The isotope with a larger binding energy contains 1 more neutron than the other isotope. Find the difference in atomic mass between the 2 isotopes. Okay, so they differ by this 1 neutron here. All right.
That's the answer.
That's the answer. That's right. Yeah.
Yeah.
So that's the answer. That's how much it differs, right? So we're going to try to work it backward, all right? So
okay.
Let's translate that to mass, okay? So 5.03 mega electron volt divided by 931.5, okay?
Yeah.
Then that's equal to about 5.4, right?
That's the difference in mass.
That's the difference in mass. So difference in mass is equal to 5.4 times by 10 to the power of minus 3. This is equal to about 0.0054, isn't it?
Yeah.
A unit. Okay, let's have a look at this again. So there's a larger, so the binding energy differ. Okay. Wonder how they work this one out though. Will, did you solve this problem as well?
No, not yet.
No? Okay. Let me think about this. So there's 2 isotopes, so they're differing by 1 neutron, isn't it?
Yeah.
So it says 1 more neutron. So that's why
he said something about like the difference of the difference or something.
Yeah. So let's take this away from the mass of the neutron here. Okay. Then that might be probably the answer. 1.008665 minus 0.0054.
Yeah, that's it.
So that's the answer, isn't it? 327.
But like, why?
That's the answer.
Okay, so that's the answer. So let's think about why that's the answer, okay? Okay. I'm just going to draw a few things. So there's a proton, 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 proton. So 1, 2, 3, 4, so that's 8 there. I'm going to draw a neutron. Okay, 1, 2, 3, 4, 5, 6, 7, 8 as well. I'm going to copy this one, and I'm going to draw another one here with maybe one more neutron here.
Okay.
One more neutron. So I want you to compare this one. So we're just going to ignore the electrons, okay?
Yeah.
So when these came together, so this is very difficult for me to explain. Just give me a second. So when they came together, they lost certain mass, right? Let's suppose that, so this is the difference in mass here, by the way. Yeah, this was the difference in mass. So when this came together, when 8 of this and 8 of this came together, mass lost is, let's say, 0.1054, okay? Unit. Let's suppose that this is the case. This one here lost, hold on. Let's suppose that this one lost, because this will lose more mass, 0, 0, and this one lost 0.1054 unit, okay? Now, let's translate this into energy. So times this one by 931.5, then you get 93 point. So the mass, the binding energy is equal to 931 point. So this is a 93.15 mega electron volt. This one here, on the other hand,
I think it's 931.5. Right?
Yeah, but I'm timesing this one by 0.1 times 1, 931.5.
Yeah.
You understand?
Yeah.
So what I'm trying to say is, so 8 of this came together and lost 0.1 U. Okay? Suppose this is the case. Then how much energy did it lose? This one translates to that much, right? Rav, do you understand?
Yeah.
Now this one here translates to 931.5 times by 0.1054.
Yeah.
98.18. 98.1801. So now, what's the difference between the two binding energies?
It's just 98.
Yeah, so 93.15, right?
Yep.
Yeah. 93.15.
So the difference in the binding energies is...
So is exactly the amount of energy that they said was the difference. How this was differing by 5.03?
Yeah.
So now, do you see that this is consistent with this case
here? So
here?
you're just gonna work backwards from there.
So I'm just trying to make some point here, so you guys can actually understand. So we start from here, right? Mm-hmm.
Right.
So the difference is 5.0. They don't tell us how much binding energy. They only tell us difference.
Yeah.
They only tell us the difference of 5.03.
So
and they only,
to do like a what?
from which we can work out the difference in mass, right? So 0.0054, which means this one lost 0.0054 more. You see that?
Yeah.
But this one has one more neutron. One more has more mass by 1.008665.
Oh, yeah. So you just
You see,
minus.
this one has this much mass more by having one more neutron, but that's not going to be true, right? entirely. We can't say that this one, you see, if they were existing as individual particles, then if this was just 8 neutrons and 8 protons, and 9 neutrons and 8 protons, then this will be heavier than this one by 1.008665, right?
Right.
Yeah.
But this one lost a little bit more mass, which is this one here. So you have to do this one minus this one. That's the reason.
So okay, you just like
So it's a little bit difficult question to understand.
yeah.
Yeah.
So how would you do it, like step by step?
So this is what I would do. All right. This is what I would do. Now you understand this one.
Yeah.
All right. The difference is 5.03 MeV.
Mm-hmm.
Divide that by 931.5 to get the difference in mass. That's how much the heavier one lost more than the lighter one.
Okay.
So the heavier one has...
Would you assign like variables for the lighter one?
Sorry?
The heavy one? Would you assign variables for the lighter one there? So say like x, let x be
Like-
lighter one,
and
let y be heavier one, and then just do like x minus y equals.
Yeah.
5.
So you don't really need the variables. I don't think you
Right.
need variables.
Okay.
So I think the most logical way of writing the solution is a difference. There is a heavier one. There's a heavier isotope. Lost more energy than lighter isotope. Is that right? Well, that's always the case. Heavier one loses more energy, true?
Yeah.
How much? 5.03 mega electron volt. Is that right?
Yeah.
How much does a 5.03 mega electron volt correspond to? This is a 0.0054 unit of mass. How do I get this one? Divide this one by 931.5. Do you understand that, Raf?
Yeah. I get it.
Yeah.
Yep. So we can say that the heavier isotope lost this much mass more than the lighter isotope, true?
Yeah. Okay. So the difference in energy.
Yeah,
loss.
but however, heavier isotope has one more neutron, is that right? Than the lighter one. Lighter isotope. So there is a gain and there is loss. Do you see that? So the heavier isotope has a 1.008, what is 655? 8665. So the heavier isotope has this much more mass because it's got one more neutron.
Oh yeah.
Is that right?
Mm.
But you don't just consider the gain. You also have to consider that it lost more mass because of the fact that there is one more neutron. So there is one more neutron, and because there is one more neutron, it lost 0.0054 of mass more than the lighter isotope. So the net gain is it's only going to be heavier than the lighter one by this much. Does that kind of make sense, Rav and Will?
Yeah.
Yeah.
Wait, what are we trying to find again?
We're trying to find out by how much is the heavier one heavier than. So what is the difference in atomic mass between the two isotopes? By how much is the heavier one heavier than the lighter one? Well, it is heavier than the lighter one, first of all, by this much. And then, because it lost this much mass, you have to take that away. Then that's how much it'll be heavier than the other one.
Okay. So you don't need to do anything very.
Yeah. So this question is actually quite hard, as I explained to you before. because it doesn't tell us how many protons and neutrons there are.
Right.
It only tells us the difference. So if it was telling you that the binding energy for this guy is 93.15 and the binding energy for this one is 98.18, instead of telling us this number, if they gave you this and this, that would have been a lot easier.
Wait, could you scroll down a bit?
Scroll down, yep.
Yeah. So how'd you get the 1.008?
Oh, that's the mass of the neutron.
Oh, okay.
Just
That's
the pure neutron.
Right.
Yeah. Okay.
Okay.
We'll move on to the next question, or
The next ones, yeah, they're not as hard. So yeah, we'll do.
the 4, 5, 6, 7, 8, they were okay?
Yeah, they're alright. Will, do you have any suggestions?
I haven't done a lot of them, but I did the first couple.
Yeah, I think all these questions are pretty easy. So have a go and let me know how you go with them, okay?
Yeah.
So this was about alpha decay and beta decay and things like that. Yeah, so also for alpha decay and beta decay, there are some mass defect as well. So here's the thing. When we talk about fusion is like this one here. This is fusion.
Okay.
This is fusion. So big individual things combined together to become something like that. Okay.
Okay.
So in fusion, let me actually draw something better. Because it confuses a lot of people in this subject. So let me go over that as well. So fusion is, you've got individual protons and neutrons like this. Okay, I should use yellow. And then when you put them together, 1, 2, 3, 4, 5, 6, 7, 8. And then in this case, 1, 2, 3, 4, 5, 6, 7. Which one is heavier? The left or right?
The left.
The left, that's right. So the scale is going to be like this, and this, and this, okay? There's like a scale here.
Is it because each of the particles have more binding energy, which is like basically mass?
So we don't really call that binding energy. So when they come together, they lose mass.
Oh, okay. So is binding energy what's holding them together?
So here's the definition of binding energy. So when this one becomes this, there's a mass defect, right? So mass defect is the lost mass. Do you understand?
Yeah.
It's the lost mass. Now binding energy is the energy. So you can calculate. So binding energy. Number one, how to calculate. That's very easy, right?
Right.
It's just the mass defect.
It must be times 931.
That's right. Mass defect times by 931.5. True.
Yeah.
Yeah. So that's how you calculate it. But what is the definition of binding energy, though? Here's the thing. When you combine all these things together, there is some energy. This is spark. This spark represents energy, all right? So the mass defect got converted into energy, and that was released, isn't it? Understand?
No.
So here's the thing. Because this energy was released, so I'm going to write it here. This energy is released, and it helps bind the protons and neutrons. Understand?
So the energy basically just mass?
Yeah, this energy is this mass defect converted into energy.
Okay, yeah.
Yeah.
Oh, okay, yeah.
So we call this amount binding energy. So here's the definition of binding energy. Binding energy is energy required to actually unbind it.
Yeah, okay.
So this is really confusing, right? So if you look at the definition of binding energy, it sounds like they're contradicting. So it's the energy that holds a nucleus together. This is equal to the mass defect of the nucleus. But if you look at another definition, yeah, it's also called separation energy. You see that? So binding energy is the minimum energy required to disassemble. So what does it mean by that? It means this. You see how when this was bound together, this energy was released, right?
Yeah.
What's going to happen if this energy comes back to this one? It's going to scatter all of it, right? Back into this state here.
Yeah. Okay.
Is that right?
Yeah.
So
So the binding energy is the energy required to separate all of this.
so in like an unstable nucleus, it's like in a radioactive.
Mm-hmm.
Is that when the binding energy is not strong enough? Or
Yeah, binding energy is so there's something called binding energy per nucleon. Have you heard of that?
yeah. Well, I think the next question after question 3 was
Yeah. So there's a binding energy per nucleon. Do you guys understand that?
Yeah.
Yeah. So let me just come back to that in a minute. Okay. So here's the idea. So when these things come together, there's a mass defect. There is a little bit of mass missing, and that gets converted into energy, and that amount we call binding energy. But the definition, the formal definition of binding energy is energy required to separate all of them. So you see, if 100 mega electron volt was released, and then this got bound together, then if you return this 100 mega electron volt back into this one, that it'll get separated. Is that right?
Yeah.
So the definition, remember, definition of binding energy is energy required to break into individual protons and neutrons. Understand?
Yeah.
Another definition is it's the energy that got released to bind. To bind protons and neutrons. So that's sort of another. So this is opposite process. But binding energy sometimes people define binding energy this way, sometimes this way here, okay? We'll come back to the binding energy per nucleon in a minute, all right?
So wouldn't the mass defect be the same as binding energy? But
Yeah, mass defect is, we don't say mass defect is equal to binding energy. We say mass defect is equivalent to the binding energy.
Okay.
Because, when you have like 1U is not the same thing as 931.5 mega electron volt, right? This is mass, this is energy, right?
Right.
Energy and mass are not completely the same. They're different unit as well. So this is mass, this is energy. But of course, mass defect 100% translates to binding energy. That's right.
Yeah.
But I'm just going to tell you something here. If you think about this is mass defect, and this is binding energy. So just going to write it here. This is very important. All binding energy are equivalent to mass defect. But not all mass defect are
Yeah, it's not-
equivalent to
okay.
binding energy.
Wait, why?
So wait, are you saying like well, like mass defect, there's more to it than there's some part of it goes to
Yeah. So
binding energy.
if you convert binding energy into mass, that's of course a mass defect. Okay.
Mm-hmm.
So what I'm trying to say is that
Oh yeah. I kind of get what you're saying.
sometimes a mass defect occurs,
Yeah.
but that's not binding energy.
Okay. Yeah.
So in this particular case, there was mass defect, right?
Yeah.
So in this fusion case, you see, mass defect is binding energy, and binding energy is equivalent to mass defect. So let me just write that down as well. In fusion, mass defect is equivalent to binding energy, and binding energy is equivalent to mass defect. Can you guys see this?
Yeah. I can
But
see it.
not in fission. Mass defect is not binding energy.
Wait, does fusion and fission have anything to do with alpha and beta decay?
So that's right. Fusion has nothing to do with alpha, beta, gamma.
Okay. Wait, can you get the thing up again so I can write that?
Yeah, I'm talking about. So in fission, it's kind of in fission or so fission is not the same thing as alpha, beta, gamma though. Okay, in fission or alpha or beta or gamma. So gamma is actually not included. Mass defect occurs, right? So when heavy stuff breaks down, or when it emits alpha particle or beta particle, there can be some mass defect. Do you understand? I'm going to draw that, but that's not, of course, that's not, of course, the same thing as the binding energy. Binding energy is a much. Binding energy is the energy that is if that goes back in, it scatters all of them back into individual particles like this. So let me talk about fission here, for example. In fission, so you have this heavy molecule, like lots and lots of things in here.
Mm.
And fission is when fission is different from alpha or beta, right? Fission is breaking into roughly two equal parts. Understand? So if this is a uranium like 235, 92, this can break into like thorium and rubidium or something, krypton and barium. Barium and krypton, okay, and two other neutrons.
Mm.
So this is going from something like this. So it looks like it's going from here to here, right?
Yeah.
So this is individual particles coming together to become this. So which one was heavier? This was heavier, right? So the before was heavier. Now, when uranium becomes these two small parts, which one do you think is heavier?
The uranium.
The uranium is heavier. So it looks like it's going against what we discussed here,
Right. Yeah.
but it still works, okay? So this one is...
Could you explain why that's...
This one is heavier? I cannot explain it, sorry.
Oh.
Yeah, I don't even know.
So is it because of the energy release?
Yeah, I haven't really thought about this one, but so whether it's a fusion or fission, reactants are always heavier than. So one explanation I can really give you here is, you see how this whole big thing breaking into two rough equal parts, but it's not breaking into individual particles, right? So if this is breaking into all these individual different parts, of course, individual different parts here, they're going to weigh more than this one here. Okay?
Yeah.
So this one doesn't defy what we discussed here, okay? On fusion. So in fission, there will be some mass defect. So you see mass defect occurs. So there is going to be a little bit of a spark energy coming out as well. So this is how nuclear bomb works. You break uranium-235 and it goes through chain reaction and you get tremendous amount of energy. But here's the thing, when this energy goes back into this one, it's just going to combine these two into this one, not break it into individual parts. So see how there's a mass defect here?
Yeah.
But it's not the same thing as. So there's a mass defect and this gets converted into energy, right?
Right.
But this energy is not binding energy, because binding energy can, when it goes back into the system, it breaks into individual protons and neutrons. But it doesn't do that. It rather binds these two together into this, and that's not binding energy. So that's one more thing that I wanted to explain. So for alpha particle, alpha decay and beta decay, I think there can be mass defect, but it's pretty much ignorable, I think.
Oh, okay.
Yeah. So you know how neutrino is such a light particle?
Yeah.
So I don't think there will ever be a question involving mass defect when they talk about alpha, beta, gamma decay.
Wait, so nothing about binding energy either?
Nothing about binding energy either.
Okay.
When you're talking about alpha, beta, gamma, I don't think they will talk about mass defect or binding energy.
Right.
So they may talk about mass defect, but not binding energy. So for alpha, beta, gamma, they may deal with mass defect, but very small mass missing, okay?
Yeah.
And of course, absolutely not related to binding energy, okay? Mass defect may show up. Yep.
Yeah, okay.
Anyway, was there determine the energy when alpha decays converts to determine, it says, so this is dealing with energy here.
Yeah.
Is it binding energy or?
So definitely not binding energy, of course.
No, it's just
Yeah, this is absolutely have nothing to do with binding energy. So what it's saying is this: there's a radium 226. The question 4. So yeah, this case is this one here, alpha decay, and there's mass defect. But that's not called binding energy. It's just energy. Okay.
Yeah.
Yeah. So here, number 4. So you got the radium 226, right? So this 226 is becoming 222 of a radon. And then there's the alpha, and of course there is a little bit of a...
Don't put the other number in below. So
yeah.
that,
So here's the thing. The original mass is how much? It's a 226 point? 02540, right? This guy is 222.01757, right?
Yeah.
So you have to measure alpha. Alpha is not going to be difference between these two. So have a look. If you look at your data sheet,
yeah.
Where's alpha? Alpha is right here, right? So alpha alone, this is going through alpha decay. It's like that.
Yeah, so is that the helium way?
That's the helium, that's right. Yeah. Hold on. We need to take care of the electrons as well. This is a helium. Or where's alpha?
I don't think we, because I think we're supposed to discount. I mean, like it's like negligible.
So alpha particle is without electrons.
Oh no, yeah, no, we use electron.
So I think we have to subtract them. Okay.
Oh, okay.
It's not negligible. It takes about this digit here. Yeah. So
I think that I think we only take them for beta.
mass of alpha particle. U. That's a 4.0012. So you see how that's different from. That's different from. 4.0015 this here. That's the mass of the alpha particle, not helium. So we're not dealing with helium. So this is helium, but this is the alpha particle. This is alpha. This is helium. Okay.
Yeah.
So anyway, we take the radon 222.01757 plus alpha 4.0015061. That's a 226.019.
And then minus
See?
it.
And then you minus that from this one. 226.02540 minus the answer. Then you get this much. And that's the mass defect. You understand?
Yeah.
But that's not binding energy. Binding energy has absolutely nothing to do with this case. It's just going through alpha particles. So this is the mass defect. This is the mass that's lost as energy. That's it. It's just energy. So you times this one by 931.5. Then you get the answer, which is, it's a little bit different, 4.87.
I think that's because you included the electron.
That's what I excluded the electrons.
Oh, okay. Really?
Maybe they included the electrons. That's why you get lower energy. So let's do it again with this one here.
Sure.
So I don't think you're supposed to include the electrons. So 222.01757 plus 4.002603. All right. So that's helium.
Yeah.
There's one more digit here missing, right? 2 here. Yeah. So you subtract that from the original mass, 226.02540 minus the answer. Then you get a lot less energy. So we got this energy before, mass before. We got a bit less mass. Times it by 931.5. And we get 4.87. So including and not including electrons makes huge difference here, as you can see.
Yeah.
There's not a negligible difference. As you can see, it's not a negligible difference. It was differing by about 1 mega electron volt. So that's a huge difference. So I still believe that you should go for this one here. So you should talk to your teacher about this.
Yeah.
Okay, because helium includes electrons. But alpha decay is purely just emission of alpha particle, which doesn't have any electrons.
Yeah.
So you shouldn't include the electrons.
Yeah, you shouldn't include electrons.
Oh, okay.
Yeah.
Okay.
Shall we call it a day? So we just said an hour today, but this is about binding energy per nucleon. Do you want me to explain what this is?
No, I think you pretty much just get as you would the mega electron volts, and then you just divide it by
for example,
the neutrons plus the protons.
Yeah. So here's the trend. So I'm going to write a trend here. The more massive an atom gets, the more mass it loses, right?
Right.
Thus, the more binding energy, is that right? So as you go up and up and up through the periodic table, when you're going down the periodic table, the binding energy is going to increase. Is that right?
Yeah.
Binding energy is going to increase. But the binding energy per nucleon is, so for example, maybe your teacher already did a good job in explaining this. So these are so this is mass number one here. So as you go up as you go up through the periodic table, you get more and more massive stuff, right?
Right.
So the binding energy for uranium is the greatest. Do you understand?
So that's why it's most radioactive.
Yeah, but the thing is, the binding energy per nucleon is you divide the binding energy by the number of nucleons. Does that make sense to you?
Yeah.
So, for example, what is the binding energy for uranium 238?
Would it be lower per nucleon?
So here's the thing. You got the this is the mass of the. So this is what I can show you. So there are mass of nucleons 238. 7.75 as 57 times by 238. So 1,801.66 mega electron volt is the binding energy to bind the 238 nucleons. Do you understand?
Yeah.
So obviously the energy that was lost, mass. So when uranium-238 all came together, so 92 protons and 146 neutrons. When they all came together, they lost 1.93 U. This is equivalent to about 2 protons, right?
Yeah.
They lost about 2 protons. Not exactly 2 protons, but they lost mass that is equivalent to about 2 protons. You see that? Or 2 neutrons. So when that gets converted into mass, it's 931.5. So it's they lost 1,801.66 energy, the mega electron volt. Well, what is the binding energy per nucleon? You divide this one by the number of nucleons. Yeah. So you see, when you divide this one by 238, then you get 7.57. So as you go down the list, obviously the binding energy so you see the binding energy is going up and up and up, right? So the binding energy is
it goes up the higher the mass.
Binding energy is going up and up and up and up, but you're dividing by the number of nucleons, which is also going up and up and up and up, right?
So the binding energy is proportional to the mass of the atom?
That's right. Binding energy is proportional to the mass of the atom. That's right.
And the number of nucleons is also proportional.
Yeah, because nucleons is also increasing. So what's going to be happening to this quantity here? As you go down the list, binding energy is going to go up and up and up and up. But of course, the nucleons is going to go up and up and up and up as well. So the pattern for this quantity here. So this is known as the binding energy per nucleon. Understand? So it shows this sort of pattern here. It goes up first and then down like this. So if you look at this graph here, you can see that the one with the greatest binding energy per nucleon is iron here. So you see how they never exceed 9? So there are many, many different atoms, and they have many, many different values of the binding energy. But when you divide all of their binding energy by their number of nucleons, you kind of get all of them below 9. So here's the thing. Why is iron the most stable one? The reason is it has the greatest binding energy per nucleon, which means in order to break this one apart, it requires, you see how in order to break this one, it requires about 8.6, right? 8.6 mega electron volt per nucleon. It requires the greatest amount of energy, doesn't it? So the one that requires greatest amount of energy to break is the one that is most stable.
Yeah.
Makes sense? But uranium, as you go down, so this is getting more and more and more going down and down and down and down. That's why, as you go down the list, they become more and more unstable. See? Yeah. But yeah, so the thing is, so there's a region of very stable nuclei here. So from about 59 to about 61, something like that. 56 to, I'm not sure. So yeah, so the nuclear instability occurs because of decreased binding energy, and there are a few other things as well.
Okay.
Strong force. So this is not the only thing that influences the binding, the stability of an atom.
All right.
Shall we call it a day?
Yeah, I got to go then. So.
Okay.
Yeah. Would you be able to email the recording?
Yeah, I'll send you the slide, and if you want the recording of today's lesson, let me know.
Sure.
Yeah.
Right. Sweet.
So it's all recorded, but only send it out if student requested, okay?
Sweet. Yeah.
Okay.
Yeah.
Thank you, Johnny.
Bye.
Thanks.